Hi everyone. So this video is an introduction to L1 regularization, and then in the next two videos we will analyze and interpret the analysis using an approximation of the cost function, very similar to what we did with L2 regularization. So just to make things more systematic, in general an LP norm is the square root of P of the sum of the pth power of the absolute value of the weights and any vector in general. So that's why the sum over I, right? Yeah. So that's why L2 regularization refers to the square root of the sum of the squares, and L1 regularization basically refers to the sum of the absolute value of the weights. Now, so basically the cost function is the same as the MLE, or the maximum likelihood estimation, plus a regularization coefficient times the L1 norm, which is the sum of the absolute value. Now, one thing to note, whether for L2 or L1, you could apply this, this norm not as in terms of the weights themselves, but the difference of the weights from a reference point. And that basically will reflect a belief that that the weight parameters should be close to that reference vector, which here we call W0, right? So this is just a side note. Now, if we want to take the gradient of this, it's a little problematic because L1 norm doesn't have a derivative, a first order derivative at every point, right? So take the extreme example. If you have just one weight parameter, then the absolute value will look like this, right? So it's not differentiable at 0. So it doesn't really have a gradient, but it has a subgradient, right? And the subgradient basically will be equal, so the derivative here equals to -1 when the value is negative, equal to 1 when the value is positive, and at 0 the average of the 1 and -1 is 0, right? So at 0 the subgradient will be equal to 0. So the subgradient is given by sign of the weight parameter, right? Element wise, right? So here if it's positive you have 1, so the sign is 1. If it's negative, you have -1, the sign is -1. If it's 0, you have 0, right? So here we are assuming that sign of 0 is 0. So basically the subgradient is given by alpha, sign of the weight plus the gradient of the original cost function, and this sign function is applied element-wise. Now note the difference, right? So in L2, that term here contained the value of the parameter, omega, right? So the larger the parameter, the value of the parameter, the larger the impact on the gradient. But here, it doesn't matter what the value of the parameter is, right? What the magnitude of the parameter is. All we care about is the sign, right? So the subgradient depends on the sign of the individual elements of the parameter, or the direction of the weight vector. But it doesn't depend on the magnitude of the weight vector, right? So it depends on the signs of the individual elements. And that will make a fundamental difference in how L2 affect the final solution, right? So here, the parameter update, I'm either subtracting or adding alpha to the parameter update. So remember, in L2, we were contracting the magnitude of the weight, right? Here I'm not contracting the magnitude of the weight. I am just subtracting a constant or adding it, which is alpha, right? In every parameter update. Now that will make a fundamental difference, as I just mentioned, and the reason is that it really matters how many of the weight elements or the weight parameters are non-zero. So it doesn't matter anymore what their values are. And that's what we will see in the next two videos, is that L1 actually promotes a sparser solution. So it promotes a solution or a weight parameter setting that has a lot of zeros. And And that will be very interesting because as we mentioned when discussing the hidden layers, this sparsity in the final solution appears in many forms in machine learning and turns out to be useful in many applications. And that's the case here for the parameter setting when using L1 regularization. Thank you.